Okay, in this video we'll be looking at section 3.4 on optimization problems. This is one of the main uses of the derivative, being able to find either the minimum or maximum value in any particular application. So I first want to start with looking at how we could construct an object with a limited amount of material, but see if we can create the maximum amount of volume. So here we have three rectangular solids with different dimensions, but notice in all three cases the bases are square, so 3 by 3, 5 by 5, 6 by 6. So we want to show that both of them have the same surface area. So in other words, both of them require the same amount of material to create. So I'm going to name these 1, 2, and 3. So for number 1, the surface area would be first the area of the top and bottom. So we have 2 squares of area 9. I can call that 3 squared. And then we have to add to that all the sides. So each side is a 3 by 11 rectangle, and we have 4 of them. So 4 and then 3 by 11. And that's 18 plus 132, which is 150. So our first rectangular solid used 150 square inches to create. Second one's a little bit easier because it's a cube, 5 by 5 by 5. So there's 6 squares in a cube. Each of them would be 5 by 5 in area. So that's 6 times 25, so that is 150. So both of these check out as using 150 square inches. And the last one, we have 2 squares, each of 36, or I'll put 6 squared. And we have to add to it the 4 rectangles that are 6 by 3.25. So 4 rectangles, each one of them is 6 by 3.25. This comes out to be 72, this comes out to be 78. So once again, 150. So all 3 of them could be constructed using 150 square inches of material. But now let's notice that they each have a different volume. So in the first one, the volume of any rectangular solid is just length times width times height. So it'd be 3 times 3 times 11. And that comes out to be 99, so that would be cubic inches. So that's how much volume, how much space is inside of that rectangular prism. The second one is, of course, 5 times 5 times 5, or just 5 cubed. And that's 125 cubic inches. So that one has more space in it, or has a larger volume. And our last one was 6 by 6 by 3.25. And that comes out to be 117 cubic inches. So far, our best option, if we only have 150 square inches to use, our best option for having the largest volume was just a cube, all 3 of them being the same, being 5 inches each. But that doesn't necessarily mean that that's the best one. Maybe somewhere between 5 and 6 is better, since 6 was pretty high as well. So an optimization problem is asking exactly that. If we have a rectangular solid with a square base, what's the maximum volume that we get if the surface area has to be 150 square inches, or that's the amount of material we have to work with. So we can first draw a picture of what this looks like in general. So our rectangular prism has a square base, so it's x by x. So notice in each case 3 by 3, 5 by 5, 6 by 6. So x by 8, x, but the last one can be different, so we'll say h for its height. So in these we want to come up with 2 equations, a constraint equation and an objective equation. So the constraint equation, as it sounds, is something in the problem that is restricting you. So in this case, it's our surface area. We only have a limited amount to work with. So what's our surface area in general in terms of x and h? Well, we have two squares. Notice in all three cases, there is two squares, x by x. So the area looks like 2x squared for the top and the bottom. And then you had 4 of these side rectangles. So in this case, it would be x by h. So you had 4xh that you had to add to that. So this expression represents the entire surface area. And this needs to be 150. So that's what we call the constraint equation. Next, we want to come up with what's called the objective equation. So objective is what we're trying to optimize. So either minimize or maximize. In this case, we want to maximize its volume. So the objective is just what's the formula for its volume. So the volume of this would be, we notice in each of these cases, 3 times 3 times 11, or x times h. So that's x squared times h. So that's our objective equation. So the goal here is we want to use the derivative, because we know if we set the derivative equal to 0, that gives us a critical value that could be a maximum or minimum, and so that might give us our solution. But right now we have equations with two variables, x and h. So we want an equation with just one variable. So we could take the constraint equation and solve for one of the variables. The easiest one in this case is the h. So subtract 2x squared, divide by 4x. You can get x is equal to 150 minus 2x squared, so that's first subtracting the 2x squared, and then dividing by the 4x. So now we have h in terms of x, so we can use that to plug into the h in the volume formula. So now our volume looks like x squared times 150 minus 2x squared over 4x. Now we want to simplify here. First, let's multiply by the x squared first. So just distribute it through. We can cancel 1 with this x, so just multiply an x to the top. So you have 150x minus 2x cubed all over 4. And we'll simplify even further to make things a little bit nicer. Divide everything by the 4. So you'd have, I'm going to do things in decimals, so you have 37.5x minus 1/2 or 0.5 x cubed. Okay, so now we have a formula for the volume. So this is still the same objective equation. It's still giving us the volume of this. Oops. But only in terms of x. It doesn't have h involved anymore. So now we can take the derivative and set that equal to 0. So the derivative here would be 37.5 minus 1.5 x squared. So we want to know when that's equal to 0. And this isn't too hard to solve. We just add the 1.5x squared to the other side, so 37.5, 1.5x squared. Divide by the 1.5, you get 25. And so x would be plus or minus 5. Now, clearly minus 5 doesn't make sense here because x is a dimension. So positive 5 is the only one that makes sense. And it does turn out that that's going to be the maximum. So x needs to be 5 inches. Well, we can already see from our example, but that it's going to be the cube. It's going to be the 5 by 5 by 5. But you could plug in 5 here for the x's here and find out that h is also 5. So that means the dimensions for the maximum volume is 5 by 5 by 5 inches. So that'll be our final answer there. Okay, so let's look at some more optimization problems. Okay. Number 14, we have a campground owner plans to enclose a rectangular field adjacent to a river, and the owner wants the field to contain 800,000 square meters. What dimensions will use the least amount of fencing? So let's draw a picture of what's going on. So we have a river, and we want to construct a field adjacent to it. So using the river itself as one side of this rectangle. So this right here is the fencing. Maybe I'll do that in marker. So this right here is the actual fencing. So we could assign some variables. If we call this one x, then this would also have to be x because it's a rectangle. And then the only other variable here is the length, the y. And so we want to minimize this. We want to minimize this total amount. We call this the perimeter. So we'll say that our objective here is to minimize the perimeter, which is 2 x's and a y. It's just the total length of fencing that we would need. The owner wants the field to have 180 square meters. So we want the area to be 180,000. So our constraint is that the area, which is just x times y, has to be 180,000. So just like before, we want the objective in terms of just one variable. So we take the constraint and solve for one of them. Again, it doesn't really matter which one you solve for, but since we like to leave things in terms of x, we'll solve for y, so that when we plug it in here, we'll have our parameter just in terms of one variable x. So we have the parameter is 2x plus 180,000 divided by x. And to take the derivative, we might want to rewrite that as 2x plus 180,000 x to the minus 1. That way when we take the derivative, so p prime, we can use the power rule there. So 2 minus 180,000 x to the minus 2. And we want to set that equal to 0. So let's move over here. And we'll rewrite this as 180,000 over x squared. Set that equal to 0. And we've seen ones like this before. We'll first multiply everything by x squared. So 2x squared minus 180,000 is 0. Add the 180,000 over. Divide by 2. And finally, take the square root. Again, we get plus or minus 300, but it's pretty clear that the negative doesn't matter here. X is, again, a length, an amount of fencing. So it looks like x equals 300. In this case, it was meters, so 300 meters will be the sides that are perpendicular to the river. And then we look back and say, well, if we want to know y, we can plug it back in to the substitution. And you get y equals 180,000 over 300, so 600. So the dimensions that we would want to use that minimize fencing will be 300 by 600, specifically the 600 being the side that's parallel, because if you did 600 the other way, it would be a lot more. Okay, in our next problem, we have what's called a Norman window, which is, you've probably seen these before. It's a window where you have a rectangle, a rectangular window, but then it has this semicircle on top. So we want to find the dimensions of this Norman window that maximize the area when the total perimeter, so the distance all the way around it, should be 16 feet. So the perimeter being 16 feet, that's going to be our constraint. So let's see if we can write down what that's going to be. well, let's get some variables here. So with the semicircle, we could say the r here is the radius of that circle. And so that would mean down here is 2r. And circumference is, if it was a full circle, it be pi times the diameter. But since we're just looking at a semicircle, it'd be half of that. But half of the diameter is already the radius. So this distance here, going around, is pi times r. And then we need another variable for the two sides here, so we'll call that x. So our total perimeter here is pi r, 2r, and 2x's. So all that together is the perimeter. And we want that to be 16, so that's our constraint equation. So what's our objective here? Oops. Well, we want to maximize the area. So we need to find a formula for the area here. So we have two things put together here. We have a rectangle and a circle. So first, the area of the rectangle would be just length times width, so 2r times x. And then the area of a circle is pi r squared, but it's half of that because it's a semicircle. So 1/2 pi r squared. So that's our objective. So you could solve for either r or x here. It's a little bit easier to solve for x. And what I did was factor out an r from these two. So I moved these to the other side, but I factored out an r first. So you'd have getting x by itself. So you get 16 minus these two. So 16 minus r times pi plus 2 after factoring that out. And then I have to divide by 2. And so that's going to go into the x here. Notice there's only one occurrence of the x in the area. So this whole expression will go in for this x here. And what's nice is that this 2 is going to cancel out that 2. So our area, I'll write it out first so we see that it's going to cancel. Let me get this canceling. Let's go ahead and distribute this r. So we get 16r. We're going to get r squared times pi plus 2. And we have our 1/2 pi r squared. So now we're ready to take the derivative. We have a function not in terms of x, but in terms of r. But there's no x's involved, so we're okay taking the derivative. So a prime, our derivative, is just 16. And here you just have r squared times constants. The pi is just a constant here. So in both cases, you just get 2r. And here the 2 cancels the 1/2, so I just get pi times r. And this is what I want to know when it's equal to 0. Looks like I made a mistake in my notes, so I'll have to calculate this a little bit over. I had the 16 gone for some reason. But yeah, 16 should still be there. So we want r by itself. We could factor out the r from these two and move this 16 over. Actually, let's move these two over. So you'd have a positive 2 and then the pi plus 2. And then a minus pi from this. All of this times r, because we're factoring it out. So it looks like we need to divide by whatever this comes out to be. So 16 divided by, I guess we can simplify, that's 2 pi plus 4 minus pi, so that's going to be pi plus 4. Okay. I guess we can leave that as the answer. I was hoping to get an approximation there. but that'll be our radius, 16 over pi plus 4. And then you can go back and find x. So you could plug this back in and see what x is. So I'll let you do that on your own. Okay, here we have another classic problem with these objective problems, creating a box out of just a piece of cardboard or a piece of material, maybe like a piece of metal or something like that. So the idea is that you have your, we're looking at a square. And what we do is we cut out corners of this square, equal size corners. So if these corners are now gone, cut out, then we have these 4 flaps that we could fold up to turn this into a box. But this box would have a bottom but no top, so we can sort of put that we can see through to the inside of it. So that's what we call this or why we're calling this a square box with an open top, or an open box. So let's give some dimensions here. We know that these are 6 each, and so there's only one variable going on here, just how much we cut, because we're cutting little squares here, so x by x squares. So if we cut these out, notice, the new dimension will be 2 x's that are cut out. So this will be 6 minus 2x. This one will also be 6 minus 2x. And the new height of the box will be x, just how much we cut into it. So what we want to maximize here, we're trying to find the largest, this should be size of a box. We're looking for the volume. There's no constraint here because there's no second variable. So we just multiply length times width times height. So 6 minus 2x squared, since we have 2 of them, times x. And so for finding the derivative, we'll need the product rule and then general power rule. So v prime, say first times derivative of the second, so 6 minus 2x squared, times the derivative of x, which is 1, plus, and then the other way around, x times the derivative here, which will be 2, 6 minus 2x to the first power, but then don't forget the chain rule part of it, so multiply by a minus 2. Minus 2. Okay, so notice we've seen ones like this before where you're starting with the power of something. You're going to have at least one of them that can be factored out. So the 6 minus 2x, there's one of them here, there's 2 of them here. So I can factor one of them out and see what we have left. We have one of them left here. And we have a minus 4x here. So if this is gone, you have x times 2 times minus 2. So minus 4x. And so simplifying there, we have 6 minus 2x and 6 minus 6x. And this is what we want to set equal to 0 to find our critical value. So setting this to 0 gives you x equals 3, and this one gives you x equals 1. Now, if we think about what x can be, well, certainly x has to be at least 0, since we're cutting something out of the box. But if I go to 3, then that's half of this already. So imagine cutting up to 3 here. You would cut out so much of a corner that all 4 corners would cut out the entire box. So there'd be nothing left if you went past 3. So x has to be between 0 and 3. And in particular, if x is 3, then nothing's left. So 3 is kind of gone here. Doesn't really matter. So 1 is going to be our answer. So 1 inch cut out of this will give us our largest volume box. And then you can plug back into the volume to see what that would be. So that'd be 6 minus 2 times 1 squared times 1. And that comes out to be 16 square inches. So you could even test out, try, if you want to do a half an inch or if you want to do 2 inches, see what volume of a box you would get. You would always get smaller than the 16. So the 16 is the best you get using 1 inch as your how much you cut out of the box. Okay, next we have a little bit more of a general problem, not really an application, but it's still trying to find a maximum area in this case. So first we have a rectangle bounded by the x and y axis by this graph 3 minus 1/2 x. So let's see what they mean by this. So 3 minus 1/2 x means that it's starting at 3, and then it has a slope of negative 1/2. So I'll just draw a line here. So that would mean it eventually will cross here at 6. If it has a slope of 1/2, 3 over 6. And so what they mean by a rectangle bounded by it means that if you create a rectangle inside here, you could create different ones depending on which point you pick. If you pick this point, then you'd have this rectangle. If you picked a point out here, you have a really thin rectangle. So this is just our general rectangle. We want to know which one gives us the largest rectangle. So one thing we can do, we could have constraint and objective equations here, but it's actually easier if we only work with x. So if this is x, this is the point x, y, but y is always 3 minus 1/2 x. So we don't have to have y involved at all. And so the area of this, this length would be x, and then the height of the rectangle would be the y coordinate, so 3 minus 1/2 x. So we have area just in terms of x, so x times 3 minus 1/2 x. And we don't really need the product rule here because we could just distribute the x, so 3x minus 1/2 x squared, and we can take the derivative from there. So 3 minus x. That one's going to be fairly easy. We just get x equals 3. And if x equals 3, y equals 1/2. Or sorry, 3/2. So x times y, the area would be 3 times 3/2, which is 9/2 or 4.5. So it has a maximum area of 4.5. But it was asking for both, right? Now it's just asking for length and width, so this would be the answer. Okay. Last one here. Hopefully I have enough time for it. It is kind of a long one. Let's read it first, and then we'll draw a picture of what's going on. So you're in a boat 2 miles down, or 2 miles from the nearest point on the coast, and you're to go to point Q, which is located 3 miles down the coast from that closest point. You can row at a rate of 2 miles per hour, and you can walk at a rate of 5 miles per hour. So how far from the closest point on the coast should you row toward in order to reach Q in the least amount of time? So a lot of stuff going on here. Let's draw a picture so we at least have an idea of what we're even talking about. So here's our river. And let's say our boat is here. And we're 2 miles away from the coast. So this distance here is 2 miles. Or from the closest point on the coast. So that would be perpendicular. And on the coast, I guess it doesn't say it's a river, so you may ignore that part, but it doesn't really matter. This part won't come into play. So down the coast, there's a point Q that's 3 miles away. Oops, not minutes, miles. So you can imagine some options here. You could just row straight towards that, but you row kind of slowly, only at 2 miles per hour. So you walk a bit faster than you row. You could just row straight to shore and then walk, but that's probably going to be a little bit slower than if you picked a point called P and first row to that point and then walk the rest of the way. So it stands to reason that there's probably an optimal point here that we row to first at 2 miles per hour and then walk the rest of the way. So let's call the distance between that closest point and the point we're going to row to x. So x miles away from that closest point. Using the Pythagorean theorem, since it's a little right triangle here, we would get that this side is x squared plus 2 squared. The square root of that would give you the length of that hypotenuse of the triangle. So that's the distance you'd have to travel in terms of x by rowing, by boat. And it's pretty easy since the entire length is 3. This distance would be 3 minus x, and so that would be the remaining distance. So we know each of the distances, and we know how fast we go on each of those distances. So we can get the total amount of time, which we'll call t, that it's going to take us. How do we find time? We have to take the distance and divide it by how fast we're going. That'll give us how much time. So we take each one of these distances and divide by the amount of time that it's taking. So the x squared plus 4, the square root of that, we'd be dividing by 2. That would give us the time for rowing. And then similar for the walking part, we'll take the 3 minus x and divide it by 4. Let's simplify a little bit. Dividing by 2, that's the same as multiplying by 1/2, so 1/2. And then we'll write this as a fractional exponent since we want to take the derivative. At 3/4 and then minus 1/4 x. It looks like I'm out of time here. I'm not going to be able to finish in this video. But the idea is you take the derivative of this and set it equal to 0. So maybe I'll finish this in another video. Okay.